Okay, so welcome to our week 5 class meeting. This meeting is being recorded. Thank you all for being here. I will go ahead and just jump right into it. As always, Amber, no, you can't hear me. Let me try in the chat. Amber, you can't hear me? So I'm going to go ahead and share my screen with you guys. We'll see what Amber has to say, and hopefully she can hear me now. So I'm going to stop sharing this. I'm going to go ahead and share my screen with you. Okay, let's see. Amber still cannot hear me. You can hear me now, Amber? Okay, great. Okay, so let's share the screen and get going. Okay, that's not what I wanted. Okay, so just like in the previous weeks, I'm going to have the chat minimized. So if you have a question, just hang on to it for a second. I'll be asking questions throughout the presentation, just like always, so there will definitely be chances to ask questions. I just don't want to miss your question because you accidentally asked it when I had the chat minimized, and then somehow it gets buried later under other comments. Okay, so if you don't already have one, we are going to be doing a couple examples today, and you're going to want to have a calculator, so please make sure you have a calculator. Any calculator is fine. The one on your phone is fine. Anything on the internet or on your computer, just a basic calculator is fine. One with fractions is ideal. Okay, so the last couple weeks, we were working a lot with descriptive statistics, and we were talking a lot about correlation and regression and different ways we could describe and compare data. Now, if you're feeling a little exhausted, just know that those formulas and all the stat crunch and all the stuff we were doing before is gonna be, we're gonna do a shift now into something that's a little bit different. Most students like the module 5 and 6 work we do much better than the module 3 and 4. The formulas aren't as bad. There's not as much extra stuff with like a computer. It's a little more like traditional mathy, if you will. So a lot of students like these two modules better than the ones we just covered. So I hope that's you. If not, I hope you like it anyways. So we're going to be talking in the next 2 weeks about probability. So the first thing is, well, what is a probability? A probability is a number that tells us how likely it is for something to happen. A probability is always a number between 0 and 1. So it's always going to be a decimal value between 0 and 1. And the way we can tell, or the way we can interpret the probability number, is a probability of 0 means that there is no chance whatsoever that the event that we're talking about can happen. It's impossible for this thing to happen if it has a probability of 0. Whereas a probability of 1 means that it's assured that it definitely will happen. 100% guaranteed, we know for sure this will happen. And in the middle of those two extreme numbers, basically if the probability is closer to 0, it's less likely that that event is going to occur. It's possible, but less likely. The closer the probability is to 1, the more likely it is to occur. So again, a probability has to be a number between 0 and 1. So if you get a question on your homework that asks you whether or not a certain number can be a probability, that's the criteria that you're looking for. So really quick, let's go ahead and go through some of these examples right here. So this first example, 0.42, could that be a probability? Yes, it can, right? That's a number between 0 and 1, so that definitely can be a probability. How about the second number, the 0.99? Could it be a probability? Yes, it definitely can. That's between 0 and 1, so it can be a probability. How about this third one? Can that be a probability? It cannot. Why can it not be a probability? What's wrong with it? Yes, it's negative, okay? So it's not between 0 and 1. So if you ever are trying to calculate a probability and the answer you get out of your calculator or your paper turns out to be a negative number, know that something went wrong. That cannot be the answer. So these are some good ways to kind of check your final answer if you're not sure of it. If you get a negative number, that's definitely not correct. How about this last number, the 1.2? Can that be a probability? No, it cannot. Why can't that be a probability? It's more than one, exactly. So likewise to what we were just saying, if you're doing your work on the homework and you're trying to find a probability of something and your calculator spits something out to you that is more than one, go back and double check your work because something went wrong. That cannot be a probability. Okay. So of those two probabilities that we had above, that was the 0.42 and the 0.99, which one suggests that the event is more likely to occur? Yes, the 0.99 is indicative that the event is more likely to occur because 0.99 is closer to 1 than 0.42 is. Exactly. Okay, so that's what a probability is. So how about a probability model? So a probability model, or another term for this is a probability distribution, is the set of all possible outcomes along with their probabilities. So if you made like a list or a table of all the different outcomes that could occur in some situation, and then next to them you listed all the probabilities of those events occurring, that would be a probability model if the following things are true. So to be a probability model, by definition, all the probabilities, all the unique individual probabilities in your set or table have to be between 0 and 1, and all the probabilities together must sum to 1. So that means that if you added up all the probabilities in the table, you would get a grand total of 1 at the end. So let's try an example. So here's a little table that shows you different sizes of maybe t-shirts or something. And to the right, it shows you the probability of someone selecting or buying that size of t-shirt. So we want to determine if this is a probability distribution or a probability model or not. So we just need to ask ourselves a couple questions. So first question is, are all the probabilities between 0 and 1? Yes, they are. So if we look at all the individual probabilities here in this table, every single one of them is between 0 and 1. Do all the probabilities together add up to 1? So this is where you're going to need your calculator. Yes, I'm getting yeses. So yes, they do. So if you throw all those numbers into your calculator and add them all up, you will get a sum of 1 at the end. So since we answered yes to both those questions, is this the probability distribution? Yes, it is. So all we have to do is meet those two criteria and then it will be a probability distribution. So let's try the next one. So now I have some colors, maybe these are of candies or something, and I have a probability associated with each color that occurs. So I want to know if this is a probability model. So I ask myself first, are all the probabilities between 0 and 1? Yes, they are. Do all the probabilities add up to 1? Exactly. They do not all add up to 1, right? If I add all those up, I get something less than 1. So is this a probability distribution? No, it is not, because both of those criteria have to be met in order to be a probability distribution. Good job. Let me see if I can move the chat up here so we can see this next example, and so I can still see what you're writing. Okay. Oops. So here's our last table. So we have 5 different events which aren't indicated in any particular way other than 1, 2, 3, 4, 5. And then we have some probabilities over on the left. On the right. So first question, are all the probabilities between 0 and 1? They are not, right? I see this guy right here, which is a negative number. So do I even need to check the second criteria? I don't even need to check it, right? I already know that this is not a probability distribution because both of those criteria had to be met. The first one failed, so I already know it's not a probability distribution. Okay, so just remember that is what a probability distribution is. And if you're asked to determine if something is a probability distribution, those are the only two things you check. Are all the probabilities between 0 and 1, and do all the probabilities add up to 1? Okay? So then, now that we know what a probability is, how do we actually calculate a probability? Well, a probability is, in general, actually a pretty simple concept. It's just a fraction where you set up the numbers in this way. On the top of the fraction, you're going to write in the number of ways that the event you're interested in can occur. So the top is going to be the number of ways you can get what you want or what you're looking for. The denominator, the bottom of the fraction, is going to be the total number of ways you can get anything in this situation. So not just what you want, but just how to get anything at all. Okay, that is basically what a probability is, and that is it. We're going to see some little nuances and formulas this week, but in a nutshell, that's all a probability is, and that's the main thing you want to keep your mind going back to as you do probabilities this week and next week. So let's try an example. So say this is a pretty simple example, but it's just to illustrate the concept. So if you flip a coin, we want to know what's the probability that will land on heads. Now we might already know the answer to this question because it's sort of intuitive, but let's see how we would work through the process mentally on this simple example, because the few questions you would ask yourself on this simple example are the same things you can apply to a larger, more complicated example. So the first thing you want to ask yourself is, okay, if I flip a coin, how many total possible outcomes could I get? I could get 2, right? I could get heads or I could get tails, and that's it. So I have 2 possible outcomes total. So second question is, if I flip the coin, how many ways are there for me to get what I want? In this case, I wanted to get heads. So how many ways can I get heads? Just one way, right? I can get heads, and that's it. Okay, so again, the probability is the number of ways to get what I want divided by the total number of ways to get anything. So the probability of flipping a coin is going to be 1, that was the number of ways to get what I wanted, over 2, the number of ways I could get anything. So 1 over 2, or 0.5. So when I flip a coin, the probability that I get heads is 0.5. Let's try another one. So let's say we're going to roll a die, just a standard 6-sided die, and we want to know the probability that the die, after it's rolled, will show a number that is less than 3. So we go through the same questions. It's the same basic questions every time. If I roll the die, how many total possible outcomes could I get? I could get 6 outcomes, right? I could roll a 1, 2, 3, 4, 5, or 6. So there's 6 possible outcomes I could get in general from rolling the die. Okay, so how many ways can I get what I want? Remember, I wanted a number less than 3. So it's going to be 2, because I said less than 3. That means the 3 itself is not included. So there's 2 ways. I could roll a 1 or I could roll a 2. And then if I apply my formula, the probability of rolling a die and getting a number less than 3 is 2. That was the number of ways I could get what I wanted, over 6, the number of ways I could get anything in this situation. So 2 out of 6, which is 0.333, repeating as a decimal. Okay? Any questions so far about what a probability is, what a probability model is, or what this basic fundamental concept of how to calculate a probability is? Okay, let's keep going. All right, so those examples were pretty easy, and some of us might have already known the answers before we even walked through the questions. So let's try an example that's a little bigger now. So say we have a group of college students, and in this group there are 4 freshmen, 2 sophomores, 3 juniors, and 1 senior. And we're going to select one student at random from this group. So let's see if we can calculate the following probabilities. First, we're going to calculate the probability that the student is a sophomore. So we go through the same questions. If I pick a single student from this group, what are the total number of things I could get? Excuse me. So this is going to be 10. The total number of things I could get is the total number of students in the sample. So 4 plus 2 plus 3 plus 1 is 10. Now, how many ways are there for me to get what I want? 2 ways, right? There were 2 sophomores and I wanted a sophomore, so there's 2 ways. So what is the probability then of picking a sophomore? It's going to be 2 out of 10. So remember, when you're asked for the probability, it's always going to be that fraction or that decimal between 0 and 1. So 2 out of 10, or 0.2, is a decimal. Okay? Let's try another one. So let's say now we want to get the probability that the student is an upperclassman. So I ask myself, what are the total number of things I could get? It's still 10, right? Nothing changed. 10 students. Okay, how many ways are there for me to get what I want? I wanted an upperclassman. Remember, an upperclassman means a junior or a senior. There are 4 ways, right? There's 3 juniors and there's 1 senior. So together that's 4 upperclassmen. So there are 4 upperclassmen, meaning 4 ways to get what I want. So what's the probability of picking an upperclassman? Yes, it's 4 out of 10 or 2 out of 5 or 0.4 as a decimal. Exactly. Let's do one more. So what is the probability that a student is not a senior? So again, I ask myself, what's the total number of things I can get? Hopefully it's clear by this point that there are 10 students, so that answer is 10. How many ways are there for me to get what I want? Amber's already got it. Yes, there are 9 ways. So the probability is? Yes, 9 out of 10 or 0.9. Okay? Any questions about any of those? Awesome. Let's keep going. Okay, so now that we know how to calculate probabilities, there's this concept of something being an unusual event. And remember, we said on a couple slides ago that if a probability is close to 0, it means the likelihood that it happens is very, very small. It's very unlikely. So something that's very unlikely to occur is unusual, right? We don't expect those events to occur very often. So the question is, how close to 0 does a probability number have to be in order for us to classify it as an unusual event? Well, we could argue about this, but people already argued about it, and they basically settled on this rule. If the probability of an event is less than 0.05, meaning there's less than a 5% chance that it will happen, we call that event unusual. Okay, so remember this rule of thumb. This is what it means for something to be unusual. This benchmark number that you're going to compare to is 0.05, okay? So here is a probability distribution where we're showing some colors and the probability of each color. If you look through the different probabilities there, are there any colors in this set that are unusual? And if so, which ones? Remember, unusual means the probability is less than 0.05. So red and purple are the unusual ones. I saw a couple votes for green. So green has a probability of 0.08. So 0.08 is actually more than 0.05, right? So you were close, but it's only red and purple because those are both less than 0.05. Okay, even though this green is very, very small, it's not small enough for it to be classified as unusual given this criteria. Okay, any questions about that? Cool. Let's keep going. All right. So now let's start talking about some of the formulas you need for this week. There are three basic formulas you're going to use this week, the big three. So this is the first one of the big three. It's called the complement rule. So before we talk about the complement rule, what the heck is a complement? So a complement of an event is basically saying the opposite of that event happening. So the complement of an event is all the possibilities other than that event. So if the event is labeled as A, then we denote it, the symbolism that we use for the complement is an A with a little C on the top. It kind of looks like the C is an exponent. It's not an exponent. It's just like a superscript to indicate that this is the complement of the event A. So for an example, say the event is that a person has blonde hair. Maybe for some reason I want to know the probability of someone having blonde hair because I need a blonde-haired person in my commercial or something. So the complement of a person having blonde hair is very simply just the person does not have blonde hair. It doesn't mean they have some specific color of hair. It could be brown, it could be black, it could be red, it could be green, but they just do not have blonde hair. Second example, if the event is that a cup of coffee has cream in it, the complement is just that cup of coffee does not have cream in it. So it's just the opposite of whatever the original event is. Last one, if the event is that a person has at least one pencil, then the complement would be that a person has no pencils, right? I either brought at least one pencil to class, in which case I can take notes, or I did not bring any pencils to class and I feel silly because now I can't take notes. Okay? So the formula for calculating complements and relating them to the probability of the original event is this one right here. The probability of the complement of A is equal to 1 minus the probability of the original event A. And also I would point out that I could have switched these. I could have had the probability of A here on the left-hand side of the equal sign and had probability of A complement here. So it works both ways. Okay, just remember one is 1 minus the probability of the other. So using these same examples we had here, if I wanted to calculate the probability of these, so the probability that a person has blonde hair is equal to 1 minus the probability that the person does not have blonde hair. The probability that a cup of coffee has cream in it is equal to 1 minus the probability that the coffee does not have cream in it. And the probability that a person has at least one pencil is equal to 1 minus the probability that a person has no pencils. Now, why do we care about this formula? We care about it because sometimes calculating the complement probability is easier than calculating directly the original probability. So if we can calculate the easy complement probability, then we can just subtract it from 1 and get the original probability that we want. So it's just a matter of simplifying our lives when possible. So now let's talk about the at least one rule. So, well, before we do that, any questions about the formula in general that we just talked about? Okay, so let's talk about the at least one rule. Someone asked a question about this in the discussion board. So if you are asked to find the probability of at least one something, whatever it is, remember this rule. This is going to show up on your homework and this is going to show up on your exam. So please make sure you jot this down and commit it to memory. So saying that at least one of something happens is the complement of saying that none of that thing happens, i.e. you either have at least one pencil or you have no pencils. So the probability of at least one something is going to be equal to 1 minus the probability of none of that thing happening. It's going to basically look like this. I want you guys to jot this down, and when I say jot it down, I mean jot it down exactly with this little blank space in here just like I have it, because this is the formula that you can use for any question that has the words at least one in it. And all you have to do is in the blanks fill in whatever the statement is that you're looking for at least one of whatever. For example, if the question said find the probability that a person has at least one parking ticket, then that's going to be equal to 1 minus the probability that a person has no parking tickets. The probability that at least one toilet works is going to be equal to 1 minus the probability that no toilet works. The probability that at least one lottery ticket wins is equal to 1 minus the probability that no lottery ticket wins. So do you guys notice in all these examples, the phrase under the phrase in the blank, the underlined portion, is the same on both sides of the equal sign. And all that's changing is on one side it says at least one, and on the other side it says no. We basically just filled in those phrases to this formula up here. Okay, so please remember this formula. We're going to do a easy example right now and a harder example later, but this is going to come up and it's very important. So let's do this example. So say that you went out and you bought 5 lotto tickets because you really are hoping to win the jackpot. Now, in one way or another, you know that the probability that all 5 of those lottery tickets will lose and you walk away with nothing, the probability that they all lose is 0.999. But you don't need all 5 of those lotto tickets to win in order for you to win the jackpot. You only need one of those 5 to win, and then you'll be a millionaire. So what is the probability that you are holding at least one winning lottery ticket? Let's see. So again, we have this formula, right? Yeah, it's pretty close, Amber. So for this formula, again, that's the same one we have up here and the same one that you wrote down and are planning to commit to memory. All we have to do is take this formula that we know and fill in the phrase that we're looking for into both of the blanks. Now, again, we were asked to find the probability of getting at least one winning lotto ticket. So I can fill in the phrase, at least one lotto ticket wins, or winning lotto ticket, or however you want to phrase it, is equal to 1 minus the probability that no lotto tickets are winners. Okay? So do we know the probability that no lottery ticket in our hand wins? What is it? Yeah, it was given, right? It just said right here the probability that all the lotto tickets lose is 0.999. Saying that they all lose is just another way of saying that none of them win. Okay, sometimes you do have to sort of translate the phrases a little bit because they might not be stated in precisely the same way in the question and in the formula, but you can intuitively translate one to another to know that they mean the same thing, right? All 5 lotto tickets lose is the same thing as saying none of those 5 win. Okay, anywho, so that probability was 0.999, so all I have to do is take that 0.999 and plug it in right here in the formula and then calculate it, and I'm done. So the probability that at least one of my 5 lottery tickets wins is only 0.001. Now, we had that criteria 2 pages ago, or maybe 1 page ago, however many. So we know that this is a very unusual event because this is quite a bit lower than 0.05. So we don't have a very good chance of winning the lottery. Okay? Any questions about that example or the at least one rule? Okay. Then let's keep going. So here's the next big formula for this week, the addition rule, or sometimes it's called the OR rule. So sometimes we want to know the probability that one event or another might occur. We'll say event A or event B, whatever those are. So for example, maybe we want to know the probability that someone has blonde hair or they have red hair. Or maybe we want to know the probability that someone is a female or they are a freshman in college, right? We want to know if one thing or another happens. So the formula for probabilities that contain or imply the word or is this. Probability of A or B is equal to probability of A, whatever the first event is, plus probability of B, whatever the second event is, minus the probability of A and B. So saying or in between these means only one or the other has to happen. They don't both have to happen. Just A or just B or both, any of that is fine. If I say A and B, that means they have to both happen at the same time, okay? So if we have any kind of a question where that word or is in there or it's implied somehow, we would use this formula. So let's take just a straight calculation kind of example. So say you're given in the homework question that the probability of A is 0.52, the probability of B is 0.41, and the probability of A and B is 0.27. So basically, we're just going to plug everything into the appropriate place in the formula. So this is the formula. So probability of A is 0.52, so that goes first. Probability of B is 0.41, so that goes second. Probability of A and B is 0.27, so that goes last, and we put in the appropriate plus, minus in the right positions, and we work it out on the calculator, and we get that the probability of A or B is equal to 0.66. So it's really just a plug and chug kind of question that you will see in the homework. So how about you try it now? Say that you're given the probability of A is 0.5, the probability of B is 0.4, and the probability of A and B is 0.2. So what by this formula is the probability of A or B? Yes. So the probability of A or B in this case is 0.7 because I took the 0.5 plus the 0.4 minus 0.2 is equal to 0.7. So simple as that. We just apply the formula and plug everything into the right place. Okay, let's keep going. So again, here's the formula up here at the top for reference. Now, the last example was a little easier because they gave us very nicely and cleanly everything on the right-hand side of the equal sign, and we just had to plug it in. But sometimes we might be given the values out of order. For example, say you're given the probability of A is 0.5, the probability of A and B is 0.2, and the probability of A or B is 0.4. And now you're asked to find the probability of B. Well, that looks a little weird because the probability of B is like stuck here in the middle of this bigger expression on the right-hand side of the equation. But that's okay. We're still going to do the same thing. We plug in all the numbers just into the right spot in the formula, and then we're just going to back in with maybe 1 or 2 steps of algebra how to solve for that missing value. You might even be able to do some of these in your head. So the probability of A or B was given here. It was 0.4, so I plug that in here on the left-hand side. The probability of A was given as 0.5, so I plug that in here. Now I wasn't given the probability of B. That's what I'm supposed to solve for, so I leave that as it is for the moment. The probability of A and B was given to be 0.2, so we plug it in right here. And if we back into this, so I can combine on the right-hand side, the 0.5 minus 0.2 gives me 0.3, and then I can just subtract the 0.3 from both sides and get that the probability of B is 0.1. Okay, so again, you're just going to plug the numbers into their right spot and then back into whatever missing piece there is from the formula. So you give it a try. So say you're given probability of A is 0.6, probability of A or B is 0.7, probability of B is 0.3, and you're trying to find probability of A and B. By plugging in those numbers to their right position and solving, let me know when you're ready what the probability of A and B is. I'm getting lots of votes for 0.2, so again, we just plug everything into the right position, and when we finally back into it, we do get 0.2. So the probability of A and B is 0.2. Any questions about that? Okay. So let's talk about what mutually exclusive or disjoint events are. So sometimes if we have two events, it is impossible for those two events to occur at the same time. When that is the case, we say that those events are mutually exclusive or disjoint. Those are just two terms that mean the same thing. So if you see the words mutually exclusive or disjoint, it just means that these two events cannot occur at the same time. So for example, if the event A is that a person is 5 years old and the event B is that a person has a driver's license, we would ask ourselves, are these mutually exclusive? So the question is it possible to have a person who is 5 years old who also has a driver's license? That is not possible, right? You cannot have a driver's license if you are 5 years old. So there is no overlap between the groups of being 5 years old and having a driver's license. So that means that these events are mutually exclusive. They cannot occur at the same time. Let's try another example. So let's say the event A is a person is a freshman in college, and event B is that a person has blonde hair. And we want to know if A and B are mutually exclusive. So we ask ourselves, is it possible to find a person who is a freshman in college and also has blonde hair? Surely that is possible, right? What? I asked the question in the opposite way of what I meant. So basically, A and B are not mutually exclusive. They can occur at the same time. So, whoops, let me minimize the chat. So when two events are mutually exclusive, again, that means it is impossible for them to occur at the same time. And like we said on the very first page, if something is impossible, that means that the probability of it happening is 0. So if two events are mutually exclusive, it means that the probability of them both occurring at the same time, A and B, is going to be equal to 0. So that's mutually exclusive or disjoint. Then we have something called independent events. So sometimes we have two events, and whatever happens with one of the events could affect what happens with the other event. So one is affecting the other. If that's the case, then we say those events are dependent. But other times, the result of one event is not at all in any way related to the outcome of the other event. In that case, we say they are independent. So let's try an example. So say that event A is that a person is male and event B is that a person is pregnant. And I want to know I want to know if A and B are dependent or independent. So the question is, if I know that a person is male versus I don't know if it's male or female, would knowing that the person is male affect the probability that that person could be pregnant? If I know the person is male, that's going to change the probability that they can be pregnant, right? So are these dependent or independent? Does being a male affect your chances of being pregnant? Being a male does affect your chances of being pregnant, right? So these are dependent. The fact that you are a male is affecting whether or not you can be pregnant. So if I just went out in the world and said, I wonder what the probability that any person is pregnant is, there could be some number and I could calculate that number. But if I go out later and I say, I wonder what the probability that a male person is pregnant, now all of a sudden that number changed, right? Now that I know the person is male, now I know for sure they are not pregnant. So the fact that I knew it was male is changing or affecting the probability of the person being pregnant. So they are dependent. Does that make sense? Excellent. Okay, so let's try another one. So say event A is I'm going to flip a coin and the coin is going to land on heads. And event B is that I'm going to roll a die and the die is going to land on 2. Are those independent or dependent? Is the roll of the die going to affect the coin flip or vice versa? Yes, so these are independent. So whatever I get from the coin flip is not going to affect the result that I get when I roll the die. And likewise, the die result is not going to affect the coin flip. So these are going to be independent. So when two events are independent, we get this formula. The probability of A and B, that means they occur, the probability that the two events occur at the same time is just simply the probability of A, the probability of the first one, times the probability of B, the second one. This is only for when the events are independent. Next week, we will talk about a slightly different formula that we use when the events are dependent. But this week we're only really worried about this formula for independent events. So one more time, if two events are independent, then the probability that they occur at the same time is probability of A and B equals probability of A times probability of B. So that leads us to our multiplication rule. The multiplication rule is basically the one I just said. When two events are independent, then the probability they occur at the same time is probability of A and B equals probability of A times probability of B. So this is the formula that we use anytime the probability wording contains or implies the word and. Again, you don't have to see the word and in there. As long as the word and is sort of implied, then you would use this formula. So let's try an example. So say we're going to roll a die 2 times, and we want to know the probability that we will roll a 3 on the first roll and an even number on the second roll. So the first question is, are these 2 rolls of the die independent? Does one roll affect the other? Or are they independent? They are independent, right? If I roll a die and then I pick it up and roll it again, the result of my second roll is not going to be affected by the result of the first roll. So these are independent. Okay, so what's the probability of the first event? That means that I roll a 3. Remember, a probability is the number of ways to get what I want divided by the total number of ways I can get anything. So right now I want to know the probability that I would roll a 3. Yes, it's 1 out of 6, right? If I roll a die, there's 6 possible total outcomes I can get. So 6 goes on the bottom, and there's only one way I can roll a 3. So 1 goes on the top, 1 out of 6. Good. Okay, so what's the probability of the second event? The second event is that I'm going to roll an even number. Yes, it's 3 out of 6, exactly. Again, it's the number of ways to get what I want over the total number of things I can get. If I roll a die, there's 6 possible outcomes total that I can get, so 6 goes on the bottom, and there are only 3 even numbers, right? 2, 4, or 6. 3 numbers. So there's 3 ways to get an even number, so the probability of rolling an even number is 3 out of 6. So then what's the probability of A and B? Well, we're going to apply that formula, right? So the probability of A and B is just equal to the probability of A, that was the first event, times the probability of B, which was the second event. So the first event we said had a probability of 1/6, so I plug that in here. The second probability had a probability of 3/6, so I plug that here, and I multiply, and I get 3 out of 36, or 1/12 if you reduce the fraction, or 0.0833, etc. as a decimal. Any questions about that? Okay, keep going. Oops. So the formula we had on the last page only had 2 events in it, just A and B, but we can actually extend this formula to include however many events we want as long as they're all independent. So I could more generally write this formula as the probability that A and B and C and D and E and F and however many you want is just equal to multiplying all the individual probabilities as long as those events are all independent. Okay, so let's have you try it now. So say that you're going to flip a coin, and we want to know the probability that you will get heads on all 3 flips. So the first question is, are these independent? The three individual flips, or do they affect one another? They are independent, right? Each individual flip and the result we get on that flip is not going to affect what I get on the next flip. Okay, so they are independent. So what's the probability of the first event? The first flip landing on heads. It's 1/2 or 0.5, right? If I flip a coin, there's 2 total results I can get. So 2 goes on the bottom, and only one of those events is heads, the one that I wanted. So 1 out of 2. So the probability that on my first flip I get heads is 1/2. What's the probability of my second event? The second event is that my second flip is heads. I see some typing, so I'm just waiting for the typing to finish. Yes, it's the same, right? I flip the coin a second time, it still has the same probability of getting heads. So the probability of getting heads on the second flip is again 1/2. Okay, how about the third event? On the third flip, I want heads. What's the probability that on my third flip, I will get heads? It's the same again, right? It's still 1/2. On every individual flip, I get a probability of 1/2. Okay, so the question said, what's the probability that you will get heads all 3 times? So remember we said on the last slide, or maybe 2 slides ago, that we didn't have to see the word and in the formula, or in the question, I mean. So as long as that word and is somehow implied, we're going to use this formula. So let me minimize the chat because now it's blocking the words. So saying that you get heads all 3 times is just a condensed way of saying that the first flip lands on heads, and the second flip lands on heads, and the third flip lands on heads. Does that make sense? So sometimes you have to extend the wording of the question to something that's maybe a little less natural for us to say in English, but is more intuitive for us to apply the formula. So the probability is just going to be the probability of the first times the probability of second times the probability of the third. So in this case, it's half times half times half, which is 1/8 or 0.125 as a decimal. Okay? Sometimes the hardest part is actually interpreting the question and knowing when to apply the word and or when to apply the word or. So sometimes if you're having trouble determining which of those things it might be, just say them both to yourself out loud and see which one makes sense. Okay? Any questions about this formula or this example? Okay. So we have now covered all the major formulas that we're learning this week. So I've just listed them all here for our reference, so we don't need to go back and forth. So we had the probability of A or B. We had the probability of A complement. I do apologize. This should be an equal sign right here. I don't know why it's just a dash. And then as an extension, we had that at least one rule, right? And then we had the probability of A and B, assuming A and B are independent. So let's see if we can use those formulas now to try an example. So some questions are going to make you use some combination of these formulas to get through the whole thing. So you might be using multiple formulas to find multiple parts to a question. Here's an example. So say that your local coffee shop sells the greatest coffee in the world. You just love this coffee. However, the service at this coffee shop is terrible, and there's a 10% chance, that means a 0.1 probability, that they're going to get your order wrong on any particular day. So we want to know the probability that you will get the correct order 3 days in a row. Okay, so we're asked here what the probability is to get the correct order 3 days in a row. But before we can start to worry about that, we probably would like to know the probability of getting a correct order on just a single day, right? So what's the probability of getting a correct order on a single day? Anybody know from the wording of the question? So I have 1 vote for 0.9 and 1 vote for 0.1. It's 0.9, right? So it's going to be 0.9. Now, again, I was kind of trying to trick you a little bit just to make a point. So you really have to pay very close attention to the wording. So here I said that there's a 0.1 probability that they will get your order wrong, right? And then here I said, what's the probability of getting the order correct? So those are different complement events. Does that make sense? An order being correct is the complement of an order being incorrect. So to figure out the probability of getting a correct order, we have to do 1 minus the probability of getting an incorrect order. We were told the probability of getting an incorrect order, that was this 0.1. So all we have to do is take 1 minus 0.1 and I will get 0.9. Anybody have questions about how that worked out or why this 0.1 was not the immediate answer to this question? Okay, so just pay real close attention to the wording. Okay, so that's the probability of getting a correct order on a single day, right? So now we want to know the probability of getting a correct order 3 days in a row. So James is way ahead of us. James, you're on fire. I'm going to go through it real quick just to make sure everyone's on the same page. So remember I said earlier, sometimes the word and or is not implied and you kind of have to intuitively think of which one is the correct one. So if I asked what's the probability of getting the correct order 3 days in a row, that means I want the correct order on the first day and I want the correct order on the second day and I want the correct order on the third day. I don't want it some days and not others. Getting it correct 3 days in a row means first day it's correct, and second day it's correct, and third day it's correct. So we would have to use this and formula right here, which is where we were multiplying the individual probabilities. Okay, so I have these 3 events, and I'm just going to multiply them. So the probability that I get a correct order on the first day times the probability that I get a correct order on the second day times the probability that I get a correct order on the third day. And remember, we've just found out right here what the probability of getting a correct order on a particular day was. Every day in this case is the same. So all we're going to do is multiply 0.9 times 0.9 times 0.9, right? Each of these individual probabilities would have been 0.9. And when we do that, we get 0.729. So there is a 0.729 probability, or a 72.9% chance that you will get the correct order 3 days in a row. Sorry, Amber, what was your question? 0.1 equals 0.10. Yes, that's correct. Anytime you have a decimal and it terminates, 7 plus 3 equals 10. Yes, that's correct. Sorry, Amber, I think I'm not understanding what you're getting at. This 0.7 right here? This 0.7 right here, I got by multiplying 0.9 times 0.9 times 0.9. So if you grab your calculator and you multiply 0.9 times 0.9 times 0.9, you should get 0.729. Do you get that? Awesome. Does that make sense why we multiplied the 0.9 3 times? Okay, cool. Any other questions about this problem, either the first part or the second part? Notice we used 2 of our formulas just to answer this one question. Okay, let's keep going then. So here's our formulas again up here at the top just for reference. Okay, so piggybacking off the example from the last page. So let's say now I want to know the probability that I will get the wrong order at least one time out of these 3 days. Now, I hope I burned it into your brain enough already. What are the key words in this question that I should notice in terms of the formulas that we've learned? What was the formula you were definitely going to memorize? At least one, yes. See, I want the probability that I get the order wrong at least one time. So if you see those words at least one, I want your brain to immediately go to this formula right here, okay? Be on the lookout for those words, and if you see them, you go straight to this formula right away, okay? Let me minimize the chat so we don't cover anything. Now remember, on the last page, we found that the probability of getting the correct order 3 days in a row was 0.729, right? That's what we just found on the last page. And then we have that at least one rule that says the probability of getting at least one something is 1 minus the probability of getting that same something. And all we had to do was fill in the phrase, the same phrase here and here, right? So what is the phrase that I would fill in here and here? I'm looking for at least one what? Yes. Thank you, Janet. Sorry, I keep coughing. I got a tickle in my throat. We were asked to find at least one wrong order, right? At least one incorrect order. So if I just fill in the blank with the same phrase on both sides, I'll have the probability of getting at least one incorrect order. That's what I was asked for right here. That's equal to 1 minus the probability of getting no incorrect orders. Now, do we have or could we find this probability of getting no incorrect orders? What's another way of saying we got no incorrect orders? Yes, Janet, you got it. So saying we got no incorrect orders is just a different way of saying all the orders were correct, right? No incorrect is the same thing as all correct. See what I mean? So we just have to translate the English sometimes to make it fit to what we're looking for. Well, we just found on the last page the probability of getting all the orders correct, right? That probability was 0.729. So this is the probability of getting no incorrect orders on those 3 days. So all I have to do is take that number, which I already found, plug it into this spot in the formula and work it out, and I get 0.271. So there's a 0.271 probability that you will get the wrong order on at least one of the 3 days. Questions about that? You will get a homework question where in like part A, they ask you for some probability like we did here. And then in part B or C or whatever it is, you're asked to find the probability of getting at least one something where you will use this probability that you calculated in part A. But you might have to kind of mentally translate the phrases to see how this phrase and this phrase are actually the same thing. I think, yeah, James, I think it's one of the ones at the end. No, I can't remember which question number it is off the top of my head. But anyways, you are going to see a question that's very similar to this. So please ask if you have any questions about it. Any questions about this example, either the part we did on the last slide or the part we did on this slide? Okay, well guys, we are right at the hour and we are done. So that was perfect timing. That's it for this week. It's basically going to be those 3 formulas that we had on the top of those pages. And the biggest issue in this set of sections usually is just translating the English phrases into what you need to make one of those formulas fit. If you get used to translating the phrases, then usually the numbers, especially if you're using a calculator, which you should be, then it is not so bad. So those are all our concepts for this week. Before we turn it over for the night, any questions about anything tonight, anything from the homework, anything you saw in your reading, anything from a prior module, or anything at all? Yes, Miranda, the formulas. So the reason we used StatCrunch so heavily in the last two modules is because the formulas there are just bananas. They just are so long. They take so long. They're not hard, really. I mean, it's just basic steps. Add this, multiply this, whatever. But they're just so long. And it really is a bear to do them by hand. So these formulas are much, much easier. Amber, you do better in Excel than StatCrunch, you mean for the previous module? If you want to stick around, I will show you how to use StatCrunch because, I mean, you can use whatever you like, but Excel is a lot more cumbersome to use. StatCrunch is just like 3 clicks and it gives you practically everything you need. So it's totally up to you what you want to use. But let me show you StatCrunch before you sign off today. Before we back into the last section to do that, any other questions from anyone about the Module 5 material? Okay. Oh, I see typing. Yeah, it tends to make much more sense when we're not tired, right? So as always, this is going to be recorded and the slides will be posted. So if you are feeling tired, just go ahead and go back and rewatch it when you have time. Print out the slides, take notes on the slides so you have it all kind of in one place. And hopefully that'll make it easier when you get to your homework. You bet, Janet. Thank you for coming. Okay, folks, so I don't see any more questions about Module 5. Amber and I are going to go look at some Module 4 stuff just to review that for people who are catching up. So if you want to stick around and see that, that's great. If you're done with Module 4 and you are have no questions about Module 5, then you can go ahead and sign off. You guys have a great night, and I hope I will see you next week. Oh, real quick. Oh, some people already logged off. Well, I'm going to post this anyways, but next week, our class meeting is going to be moved to Thursday, okay? I'm not going to be able to come on Wednesday, so just for the 1 week, we're going to have our class meeting on Thursday. And as always, it will be recorded and posted, so if you can't attend live for some reason, then for sure you will still not miss anything. Sorry about that, just for this 1 week. Oh, well, good. Works out for Chase, so that's good. Okay, guys, thank you so much. So Amber, which let me go to that homework, and could you type in the chat which question you'd like to do, or do you want me to just pick one? Oops. Number 14? Okay. 14. So this is from Module 4. Okay. So Amber, I'll do this one for number 14, but basically the steps are going to be the same for pretty much every single question because there's only one spot in StatCrunch that gives you all this information, but it gives you everything as like one package. So no matter what you're looking for, you're going to be doing this. So you see up here, it says click the icon to view the data table. So if you click on this guy, it's going to open up the data table. And then if you click on the little blue icon that's on the top right, you can select Open in StatCrunch, and it should open up right for you. So let me close this. Just trying to get it so we can see both sides. Oops. Okay, so what they're asking us for here is the least squares regression line. Okay, so you have these number of, what does it say? Colas and then bone mineral. So to find the least squares regression line or the correlation coefficient or basic or the scatter plot or pretty much anything you need for module 4, you're going to do these steps. You're going to go to stat at the top, then you're going to select regression, then you're going to select simple linear. Okay, so stat, regression, simple linear. Click that, and it's going to open up this little box for you. So you just need to tell it where the two variables are. So the x variable is going to be the guy in the first column, and the y variable is going to be the guy in the second column. So you just go to the drop down and select the first column for x and the second column for y, and that's it. So if you click compute right here, you have everything you need for these questions. Okay, so the least squares regression line, that is this guy right here. Now instead of saying x and y, they're going to use the actual names of the columns. So again, trying to show you all this on one page, not having much luck here. So the number of colas, that was the x. So see how you have this number right here, and then it's times number of colas. So that's the same thing as saying this number times x. And notice the same number is down here. So if you prefer, you can look at this little chart down here if you don't like the way that it's displayed in this like equation up here. And this number is the intercept, the number that's not multiplied to x, and that same number is right here. So all you have to do is come over here and notice you have all these options, right? So one of the numbers is multiplied to an x, that's the first one here, and the other number is by itself, it's not multiplied to an x. So this one here that says intercept, that's the one not by the x. The one that says slope, that's the one by the x. So in this case, it's got to be this letter D, because the negative 0.0029 is times the x. That's the slope that you see right here. And then the 0.8862, this guy, is the one by itself. So it's got to be D. The other things you're asked for this week that you could find here are the R value, the correlation coefficient. So that's this guy right here, R correlation coefficient. So if you're asked for a question that asks you for either R or for the correlation coefficient, it's just this number. If you're asked for the sum of squared residuals, that's this number. And if you're asked for a scatter plot, see how there's little arrows down here? You just click the arrow to the next page, and there's your scatter plot. Okay? So literally everything is just in that one section. Yeah, so see, it's pretty easy. I posted, if you go to either the announcements or the discussion board for week 4 and you print out or bring up the slides that we had from that class meeting, in one of the last slides, maybe second from the last or something, I made a little like cheat sheet for what, this display looks like, and I just highlighted the 4 different things, because there's a lot of stuff going on here, right? So I just highlighted the 4 different things that we use for this module. So it's the R value, the correlation coefficient, these 2 numbers, which are what go into your regression line, or this number for the sum of squared residuals. Just those, that's it. And then the graph also. Yeah, it takes a really long time when you don't use this program, and it takes virtually no time when you do use it. So does that make sense? Would you feel more comfortable using it now? Now you're tired. Okay, well maybe not now right this second, but tomorrow maybe. Okay, sounds good. Any other questions? Okay, great. Let me open this back up. I don't know if anyone's still here. Miranda, did you have any other questions before we hop off tonight?